Okay, so hello everybody. I'd like to welcome James Osborne from the Centre for Advanced Instrumentation in Durham. He began his PhD in Durham before moving across to work in artificial neural networks for adaptive optics. He's then moved back to Durham, and since then he's been working on scintillation and developing turbulence models for the ELT. And currently he's helping to lead the optical FP7 and Horizon 2020 task for turbulence characterisation, along with the AO networking work package. And today, he's going to speak to you about characterising atmospheric turbulence for advanced optical astronomical observations. So, James.
Thank you, Rob. Can you hear me? Yeah. So we're talking about the Earth's atmospheric turbulence here, not some extrasolar planet. But as this is an instrumentation talk, I thought I'd start by telling you about my personal motivation for working on instrumentation. And it really spawns from astronomy, actually, the exciting astronomy that's going on at the moment. So, for example, here I show here's an image from SCIDAR on the VLT of a dust ring around a distant star. When we look at this image, we see that it's not just a camera put on the back of a telescope, but it has structure to it. And the first thing we notice is that the star is black, right? It's behind some corona. You also notice that there's some weird structure in this image, which suggests there's been some post-processing going on. And that means in order to get to this next level of exciting astronomy, we really need to think about the instrumentation, right, and how we do these things. And I've shown that here with a picture of the future European Extreme Large Telescope, or just the ELT, as it is now. It's been rebranded. But this could be any large telescope. So the first half of my talk, I'm going to tell the story about turbulence characterisation for large telescopes, and I'm using the ELT as my demonstration. So if we take our large telescope and we put it on top of a mountain, which is where all the telescopes go, and we look at some stars, okay? So we have the stars in the sky and we form an image over here, and this could feed an imager or a spectrograph or whatever we want. It's all the same to this focal point. And if this was all there was to it, actually life as an instrumentation scientist would be fairly easy. But it's not, because we're at the ground, so we're looking through atmospheric turbulence, which I'm showing here as this big cloud drifting across. And that has several effects on our image. So we see that down here we might have some moving around in tip-tilt, you could call it. The stars perhaps change size, maybe there's some focus there, and then there's some higher order terms as well, with some weird stuff going on. These could be stars or galaxies, just to show what's going on. Also, we notice that they're changing in brightness, they twinkle, right? This is scintillation, all well aware of that when we look at the stars, they tend to twinkle. So the question is, what can we do about it? And that's where adaptive optics comes in. If we first, okay, we'll go into some more detail then. Here's a simulation which I've run of an image of a star. And we see that it's doing exactly the same things that it's going on down here. It's moving about in X and Y, it's changing in size, it's changing in brightness, but also you can see there's some chromatic aberrations here as well. It's the different colours that are being split out. That's a problem for our systems as well, for our instrumentation. The other issue we have is the scintillation, the change in intensity. So this is the intensity pattern projected onto the pupil of the telescope. We see these flying shadows which are caused by the light self-interfering through the turbulence into the ground. And as these flying shadows enter and exit the pupil, the integrated turbulence changes, the integrated intensity changes. And this is a big problem for high precision times of photometry, for example. It's another thing that we're actively trying to solve. So, to go back, how do we solve this? Well, the first thing we look at is adaptive optics. So if we use one of our points as a guide source or even a laser, then we can correct along this line of sight, correct this turbulence that we're seeing here, and we stabilise the position in the field at that point. But these other two stars, sort of off-centre in the field, are not corrected. And that's because we have this volume of turbulence here that's not sampled by our probe, so we can't correct for it. So what do we do about this? Well, the solution is actually fairly simple. We have more lasers. If we have more lasers, then we sample all that turbulence, which means we can build a model, called a tomographic model, build a model of the turbulence above the telescope, and then we can stabilise the position of these three stars. Galaxies, whatever we're looking at. Interestingly, though, and importantly, it doesn't stop the scintillation. In fact, in some cases, the AO system actually makes scintillation worse. Okay? So in terms of turbulence characterisation, really it comes down to two sets of things we're trying to do. The first set is for site characterisation and instrument development before we're actually on sky. And the second set is for on-sky support. So, for example, PSF reconstruction or for wide-field AO, the important thing is actually the robustness that it works. And all of these things come into pre-computation of our Numerical structure, which is basically building an abstract model, calibration, optimization, performance validation, all this kind of thing. Turbulence forecast as well. If we can forecast what our conditions are going to be like, then we can schedule all our most sensitive observations at the optimal time. Okay? And then again, in terms of dosing, it's quite a big one at the moment because we have these huge domes and we have no idea what the turbulence structure is like inside that dome. So we need ways of measuring that and perhaps, if not correcting for it, at least understanding it and trying and minimising it. And then again, scintillation noise for time of photometry is a big one that we're trying to solve. So, I'm now going to go through just a couple of these and explain in slightly more detail. If we look at two sites, which I've got most of my information from, one site in Chile, which is an inland site, is the VLT, Very Large Telescope, EXO site, and Amazon is only 20 kilometers away. It's not actually in this picture, it's that direction. And then the other is an island site, like the Palma. It's a photo of the Palma. Maybe the site of the TMT, but that's still undecided. So let's look at these two sites. If we just look at the integrated seeing, which you get from a DIMM, or you sort of seeing monitor, we see that the median seeing is actually very similar, 0.665 seconds compared to 6.655 seconds. If we look at the histogram, the distribution of the seeing at these two sites, we see that actually at parallel perhaps the mode is slightly better, but then we have this weird thing at the Palma where the median is quite low, but then we have this second bump here where we seem to have a bimodal distribution and significant amount of time with bad seeing. So just looking at this, there's perhaps not much to choose between the two sites. It's only when we start looking at the turbulence profile, the distribution of the turbulence as a function of altitude, that we can understand more about these sites. So here I show two fairly complicated looking plots where we have a fraction of turbulence as a function of altitude, the parallel on the left and the parallel on the right. And the green line is the median, and then the colour is the distribution. So the broader this colour here, the more variability there is. So for parallel first, in the ground we have perhaps 25% of the turbulence in the first few hundred metres. This gradually increases, so we have perhaps 50% of the turbulence in the first kilometre and a half, say. We also see quite a bit of variability in the fraction of the turbulence below 10 kilometres, say, which suggests that the profile of hook parallel is variable, but it changes. Okay? In the Palma, we see a very different thing. Okay? In the Palma, we see, again, in the very first couple of metres, perhaps 25% of the turbulence, but then by the time you get to 500 metres, you're covering 50-60% of the turbulence. So this is, the Palma is an island site, it's very ground dominated, and the width of this colour here is quite narrow, suggesting that there's not actually much variability, that the atmosphere is more stable above the Palma. Now this is significant impact on where we perhaps want to build different instruments. Okay, so if we look at our wide field modes for adaptive optics, we've got a few choices. There's a whole array of different things we can do with AO. We have ground area adaptive optics, which can either be tomographic or just field averaging, but either way, we're just correcting for the ground layer. So something like GLAO on the Palma is a brilliant idea. On Paranal, perhaps less impactful, but still, you can still get a 50% increase in or reduction in the max or whatever. For LTO, we're looking at narrow field of big targets, perhaps either side there. If you're doing an LTO instrument, then it's less important because you can correct for a narrow field of view. For MCAO, you need a very stable turbulence significant fraction of the time. If your turbulence profile is constantly changing, then trying to optimize your NCO system to give reasonable results is actually very difficult. This is a problem that they're having at Gen Gen works incredibly well when it works, but quite often it's just really difficult to close the loop and to get it working optimally. And that's because if the turbulence profile, if you don't have a turbulent layer at a particular altitude of your VM, then the performance is limited. And for multi-object AO, this is similar to LTAO, I suppose, but in many directions at the same time. So again, parallel doesn't really matter. You can get that working at any particular site. Okay. So then to what we actually use the turbulence profile for in real time, we can use it for LPG or some predictive AO controllers. So this is an experiment that we did in Canary on an AO testbed on the William telescope in the Palmer. And here I show that R-naught is basically the amount of turbulence from a lot of turbulence to not much turbulence against the strain ratio, which is a metric of the performance of the system, a Heidelberg in this case. And without taking into account the turbulence profile, we get this orange line which has better strain ratio, as the ceiling is better, that's obvious, we expect that. If we include the wind profile from SCIDAR, from an external profiler, then we can improve that strain ratio by plus 5% in some conditions. But either way, by including in terms of PSF reconstruction, this is quite a big thing at the moment, particularly with NCO systems, which notoriously have different PSF across the field, so as you look in different angles, the PSF changes. So trying to reconstruct a PSF across that field is actually rather difficult. And it's essential for high level resolution information, basically, for photology and astrometry in private fields. Now, if we know the turbulence profile, we can estimate the residual wavelet error and try and build a PSF reconstruction method from that. This is ongoing work, and I don't have any on-scale results to show at the moment. So which parameters are we actually talking about when we're talking about atmospheric turbulence characterization? Well, we have the vertical profile of the turbulence strength, okay, so how much turbulence there is at individual altitudes as we go up. But also the turbulence velocity, and that's what I was discussing just briefly before when it comes to the predictive type AO controllers. The outer scale is also very important. So the outer scale of the turbulence is the largest spatial scale that we see the turbulence on. And that has a significant impact on both the robustness and optimization of the AO performance, as well as the PSF reconstruction. The vertical profile of the sodium layer I'm including here, that some people wouldn't include in the atmospheric parameters, but it is in the Earth's atmosphere. So when we use laser guide stars, we're exciting the sodium atoms in the sodium layer in the atmosphere, about 90 kilometers. And then we're looking at that with our wavelet sensor, which is usually an array of lenses array. We make small images and we look at how does images move and use that to reconstruct our wavelet. So if our sodium layer changes, it then becomes difficult to get the centroids and to get the local gradients across our wavelet sensor. Local dome turbulence, as we suggested before. Forecast parameters, so this is what we actually want to do with them then. If we can forecast these in advance, it means that we can take a step towards Q scheduling, which is smart scheduling of our observations. And then the temporal evolution of these parameters is also extremely important because on an ELT scale, building a tomographic constructor, building this atmospheric model is not trivial, it's really hard to do. And if we have to do it every 10 seconds, well at the moment that's impossible. If we have to do it every half an hour, we can do that. So trying to work out the temporal evolution of these parameters is particularly important. So what do these look like? Well, the atmospheric turbulence happens on local and global scales. Here's a CFD model of the TMT, actually. Where the colouring indicates the temperature of the air. So we see this really complicated structure within the turbulence zone. Outside the telescope dome, outside the telescope dome, it's less complicated, but trying to measure what's going on in here is extremely important. The other scale then is we know that turbulence is generated by wind shear or temperature differences in air mass, and that comes from weather forecasts, right? It comes from weather systems, and weather systems are global, they're big spinny things that churn around the globe. So here I've taken the wind velocity, pressure, and temperature as a function of altitude from ECNWF data from normal weather forecasts, and I've put it through standard turbulence equations, and I've generated the integrated CN squared, or seeing, sorry, integrated seeing as a function of the whole globe throughout 2015. And we can see that these structures, they move around the globe, and you can see them coming from days in advance. You can see when it's going to hit power now, and you can predict it, you can see it. So this also means that it doesn't have any site-specific calibration, because it's valid everywhere on the globe at any particular time. And we can do it in advance, very simply. What does the turbulence profile look like? Well, here's turbulence profile that I measured and the plan actually. And here we've got time for the light, it's altitude, and the colour indicates the turbulence strength. So we can see that the ground layer, as we saw before in our histograms, is very strong. This is a log scale as well, so the first few hundred meters is extremely strong in the power, and above that, all this is quite weak, but it's also very complicated. Okay, there are layers here that just disappear, there are layers that change in altitude, they come and they go. So if you optimize your AO system here, for example, you put something in your model that's got a strong ground layer, that's fine. You might put something up here, and then half an hour later, you've got a completely different turbulence profile. You have to rebuild your AO control system. In terms of wind velocity, that's also extremely variable. So here I've overlaid the wind velocity vectors on the turbulence profile plot from before, so it's just time against altitude again. You can see that in some cases the velocity just changes as a function of time. And that's then a problem for your predictive control for your LQG as well.
What's the absolute scale?
Sorry?
What's the absolute scale of the velocity vectors?
Oh, sorry, yeah, I haven't got that up here. But up here they're about 30 meters a second, and down here 5 to 10 perhaps. Yeah. Actually, in power and action, we see wind velocity of 50 meters a second at 10 kilometers. Really fast sometimes. Really fast. For outer scale, this is from simulation. So I have two wavefront phases, one with a large upscale, so we can see that there's a lot of structure on large scales, and this is a meter across here. And then again, if we restrict that outer scale to make the outer scale smaller, then we see less structure on large scales, just a small scale structure, and that has a big impact on our PSF. So the PSF goes from something big like this, something small like that. So trying to measure the outer scale is actually a really hard thing to do, and it's something which is an outstanding problem. No one really knows how to do this. We have ideas to do it with our AO geometry, but you need large baselines in order to measure large baselines. And our telescopes at the moment are about 8 to 10 meters, and we're talking about scales of 25, 50, 100 meters. So this is an outstanding problem, and it's partially the reason the PSF reconstruction is struggling. In terms of sodium layer profile, we have something like this. Okay, so this is from Canaries. This is on-sky data, and on Canary we have such that we have a natural light star with these nice little points on our Characterising waveform sensor. We also have a sodium laser, which is launched from 40 meters off axis, so it's replicating the geometry of the worst case of the extremely large telescope. And we have these really elongated slots. So the challenge is to centroid the position of each of these slots. Right? Now, in the transverse direction, that's fine, you can do it, but in longitudinal direction, you can't. So the usual way of doing things is with a match filter or a correlation waveforms sensor, for example. But that then depends on the profile of the sodium layer itself. So on Canary, we also have a sodium layer profiler, which is a 2.5 meter telescope, 400 meters off axis, all looking at the same laser eye star, and all synchronized with the waveform sensors, so we know what the truth is for this experiment. And here's an example. It might look a bit like this on our detector. This is obviously squashed down, the aspect ratio is a bit off. This is 2,560 pixels against 64. But it looks something like this plot in the middle generally. But what we do see is that it changes a lot and very quickly. Okay? So this is 1 hour of data. Color indicates the strength of the sodium return. And here this is relatively quiet. And then we have this something happens up in the high atmosphere. And we get large returns from the sodium layer at this end later in the evening. And it's not even standing calcium or anything like that, but it's a structure. There's stuff going on there, there's weird extra little bits, and all that must be recorded, somehow noticed by your AO system and used for the wavefront testing.
But does laser just make short or it lights, it emits continuously?
This is continuous. Yeah, you can use a pulse one. That's what I did to install the profile of something we're looking at. Yeah, that's entirely correct. So how can we get this information then? Well, there are 3 ways of really doing it, which we've touched on already. We can use a dedicated profile instruments. This is external to our dome, to our AO system, to our large wobbly telescope. So it's an independent measurement, which means that it's probably easier to make more reliable, more precise. But it's a different line of sight, so is that valid? If I've got my profile looking over there and my large telescope is looking over there, do we know for sure what the difference in terms of profile is? Does that matter? Okay, we can use the numerical model, we can use the forecast to try and generate our turbulence profiles, which is very convenient, right? It'd be brilliant if that just worked, wouldn't it? Just using the computer and we'd get our turbulence profile. But that still waits for a validation. There's been no real evidence that this is giving a good enough answer yet, though it's definitely going in the right direction. There are resolution issues, so your numerical model is only as good as the data you put into it, really. Ideally, we would use the telemetry, all the wavefront sensor data, all the information that's coming out of our AO system, because then we're looking along the line of sight. We're actually looking at all the stuff that's in our way, in the way of the telescope. But that's complicated, especially on large telescopes which are wobbly, they move around, they get blown about by the wind. There's lots of calibrations, there's issues with convergence. On a large telescope, you need to average over several minutes of data, perhaps 10 minutes, half an hour of data, by which time returns profile has changed. So all of these different methods of measurements, the source of information, are useful, and they all have good points and bad points. And actually, the answer is probably some combination of all of them. But for the remainder of the talk, I'm going to go through each of these in turn and just show where we're up to in Durham at the moment. It's not to say it's the state of the art in the world, but it's what I'm personally working on. So to start with the turbulence profilers, and this is mainly done in collaboration with ESO. Okay. So we go back to our cartoon where we have the ELD or any large telescope, and it's laser guided stars doing its thing, and then we have a separate telescope looking at 2 bright stars in some other direction. Okay? What we do is we look at the aberration as it's projected onto the ground from 2 different stars. Okay? So if all the turbulence is at the ground, and if you look in 2 different directions, the aberration would be the same. If the aberration is at some altitude, phase, and the turbulence is at some altitude, then the aberration that's projected down will be offset by some amount. So when we calculate the cross correlation to projected aberrations, then the offset from the centre tells us the altitude of the turbulence, and the magnitude of this peak in the covariance function tells us the strength of the turbulence. Now this can be either phase from a wavefront sensor, in which case it would be something like AO system is measuring, or it can be scintillation, right? The intensity patterns that we saw before on the telescope pupil. And when we do this, if we calculate the cross-covariance function, this is the simulation. If we have 2 layers, we get something like this. We get a nice peak in the middle, so that'll be our turbulent layer at the ground. And then in the direction of the separation of the 2 stars, which in this case is straight up, we get another covariance peak, you can see it, which is from the high layer. Okay, so that's what it looks like. In reality, it looks something like this. Okay? So this is real data from Parallel. You can see this strong peak in the middle. This is from the ground. And then this continuous streak of covariance peaks going up here is a turbulence profile. So each one of these little peaks is a turbulent layer, or perhaps we could say it's just continuous. Okay? These are the pupil images. This is actually a simulation, not real data. is the instrument that I built. And what we do is we take the two stars and we separate them with a reflective kickoff, and that way we can get the two stars completely separated even with the pupillages. The traditional general SCIDAR they're actually overlapping, which then limits the sensitivity and precision to which you can measure the covariance function. So, using this, we can also get the turbulence velocity, because we can calculate the covariance function with one frame with some delay. And the more delay we add, then these covariance peaks move. And the rate at which they move tells us the velocity of the layer. So we have this one in the middle, and that stays in the middle, which suggests it's not moving. That's within the dome. That's how we measure our dome turbulence. And we can use exactly the same technique as a dedicated dome turbulence monitor, which is a small telescope, looking at this tiny little peak right in the middle and ignoring everything else. If we look at the other ones, we see at the ground, we've got another strong layer that's going quite quickly. And we've got a strong turbulent layer up here, which is about 10 kilometers, which seems to have some dispersion to it. It's got an arc in it, which suggests that the velocity is actually dispersed within the turbulent layer. And if you wanted to look at a few examples of interesting things that we've seen in real data, from the SCIDAR velocity measurement, you can look at these frozen examples. So in the middle is our dt equals 0, our zero offset frame. And then we have some plus total offset and minus total offset, and we add them together. So in this one, we see that the profile looks like there's a single turbulent layer. If we look in the velocity space, we've got two layers which are overlapping within a couple of meters in space, which suggests we've got two distinct turbulence vectors, velocity vectors, and one turbulent layer. So if you're trying to do something with predictive control, for example, this is a big problem. We also see velocity dispersion, which is what I suggested a minute ago, with these arcs going. So the arc moves across, it looks like one turbulent layer, but it's actually a large dispersion, a full distribution of turbulence velocities. And this can be 15 to 20 degrees in terms of dispersion, which suggests we've got two air masses moving with differential velocity, and we've got some distribution of turbulence velocity between them. In reality, this is what it actually looks like in frozen frame mode, and you see how complicated it is, right? There's so much going on. So I don't think we can realistically say that we have a turbulent atmosphere with two layers or three layers and they move with this velocity. Actually, it's a whole bulk of air, right? This is a huge dynamic system. It's moving in complicated ways. And that's shown out by this information where when we have this sensitive information in terms of profile, we see there's so much going on. Okay, so here's a picture of the instrument. So there's the SCIDAR, this is the important bit of the picture. After parallel, and we have this is the AOF behind. Can't really see on this projector, which is a shame. This is the data that comes from the SCIDAR parallel. We measure R0, fraction, the ground layer at different altitudes, integrated seeing, wind direction, and wind speed as a function of altitudes too. And then we've got the profile as it evolves through the night. So the applications for this is not only for instrument design, which is the phase we're in at the moment. We can't really get in 4 or 5 hours of data per month, so we have a vast archive of terms profile data if anyone's interested in looking at it from Parallel, which is only 20 kilometers from Arizona, it's the site of the ELT. But it's also useful for performance monitoring with the AOF facility on the VLT as well. So the status is, as I say, we have 4 to 5 nights for Parallel. We also have a large archive from Canary on the planet, where we had perhaps 3 or 4 years worth of data. And it now looks like the TNT are reassessing the decision to go to the planet. So this data has suddenly become active again. If anyone's interested again, that's public and we can share that data. And the plan is to have a community data release of all of these turbulence profiles from the various sites. The other instrument that we built in Durham is a surface layer sonar. Here's a picture of the surface layer sonar. So this is a small 16-inch telescope. It's got 2 cameras on the back. It's a similar design as a SCIDAR and a pick-off. But this time we're looking at the phase, so we have a shutdown waveform sensor on each arm. And doing that, we can, because we're looking at really wide binaries, we resolve at 10-meter resolution in the ground area. So this is only the turbulence up to the first 100 meters, and we can see this exponential decay in the model. And this allows us then to estimate the turbulence from any altitude within this range for the first 100 meters. So as an example, if we take the seeing from the DIMM, which is the black line, and the seeing from the SCIDAR, which is the red line, they don't really match, right? Because the SCIDAR is on this tower, which is 2 meters off the ground, and the DIMM is 6 meters off the ground. So the DIMM's seeing more atmosphere, and the ground is very strong. You know it's got this exponential decay. So we expect the seeing in the ground to be on the SCIDAR to be worse than the DIMM, we can slow it down. However, because we have this high resolution, we can actually estimate the seeing at the altitude of the DIMM. And when we do that, we get a very good match. So this suggests that now we can estimate the seeing from one of the UTs. If you remember, observation required some specifications and requirements on the seeing, then we can use the system to say at the UT you're getting the seeing rather than just using the DIMM, which is an integrated measurement, and it isn't necessarily correlated with what the large telescope itself sees. So at Parallel in Chile, we have the SCIDAR that's placed over here, the 4 unit telescopes. We have a SCIDAR, which is going as well. We also have the MASS-DIMM, which is on the tower, which is a new one now, which is in a different position. And that gives you the integrated turbulence strength, the seeing, which we just discussed, and a low resolution turbulence profile for the MASS-DIMM. So now we have all these systems, all that parallel, all in the same place. It's a great opportunity to compare them and make sure that we're all seeing similar things. So here's our scatter. We've got the SCIDAR and the MASS-DIMM. Different parameters. The seeing is pretty good, okay, so the MASS-DIMM is in a different position, so perhaps we'd expect it to have slightly worse seeing than the SCIDAR, so that's okay. Atomic angle. There's a bit of a surprise here, but generally there's a low bias. The free atmosphere seeing is an interesting one. Okay, so the free atmosphere seeing of the MASS-DIMM is considerably lower than we get from the SCIDAR. And this has been seen before in other studies, so it looks now that actually there is some potential estimation coming from the mass. And this is an instrument that's been used in all major observatories around the world. And again, coherence time, there's a bit of a bias, but a good correlation. Okay, so to go back to the current status then in terms of external independent turbulence profile measurements, parallel, we have the SCIDAR, we have the stereo SCIDAR, which is here, which is over here. And then this is a picture taken, here's the stereo SCIDAR, one of the auxiliary telescopes. And there's Sarah Arsenis, which is the site of the ELT, not the EELT, which is really helpful, just the ELT. And that's only 20 kilometers away. So with this we can suggest that the free atmosphere that we measure at now is also valid at Observatorium, which do all sorts of studies about the performance of future ELT instrumentation. The ground layer will obviously be different, and it's got to have its own ground layer characteristics which need to be measured. And all this data is archived and is available So then we come to numerical turbulence forecasts. So this way we have our main telescope, we have our auxiliary independent profiler, but we also can use weather forecasts around the world, and we can put it through our algorithms to come out with the seeing as a function of position anywhere in the world and altitude. So does it actually work? I mean, it's a great idea. Here I show the median profile of the stereo SCIDAR, which is in the region, and the ECMWF model. So this is just the European Centre for Median Weather Forecast with my turbulence model. Okay, so its input is wind velocity, temperature, and pressure. Obviously, generally, it follows the right shape here, except for the ground. And this is where we come to the problem with local turbulence and resolution, because the resolution of ECMWF is only 20 to 50 kilometers. efforts to try and include all these local structures using mesoscale models. Well developed, and they're going to use the SCIDAR data as well to do validation, but they're not quite at that stage yet. And I also showed the scatter plots from all the parameters, as we saw before. So we have SCIDAR against the model. The seeding, again, you see the SCIDAR measures more seeding, more integrated seeding. That's as expected, because we don't have this ground layer in there. And then, well, there's not much we can do about that. So the strength then of this particular technique is for the free atmosphere, which is extremely important for our tomographic AO system, because we can imagine that the ground layer is always there. We're always going to have dome turbulence. We're not going to be able to model that. So if we know what our free atmosphere seeing is, that's our residual. That's what's left over after aeration. That's what's limiting our performance. And actually, the correlation of the free atmosphere from the SCIDAR model is very good. The coherence time, fast times, yeah, okay, so perhaps this is showing that the model is very good for wind velocities, which are fast, okay, but then there's a lot of scatter at longer coherence times. Asymptotic angle, again, we have a funny shape, so maybe there's more work to be done on coherence times than asymptotic angle. But the free atmosphere seeing is coming out quite well. And this has actually been developed at ESO. And if you go to ESO and you look at one of the control panels in the control room, you'll see something like this for the coherence time, where the black is from the mass, okay, and then the yellow and green are from the models. And they, on average, seem to give a good indication of what the coherence time will be through that map. So if we can predict this in advance, then we'll know perhaps we don't want to do extreme AO, but we have a very short coherence time. Now we know it works in the median, but what about on individual nights? And so these are individual profiles, just a few 6 selected randomly. Again, we have SCIDAR in green, and then the model in red, and the colour indicates the interquartile range. And we see generally, it works pretty well. If there are features, the model picks out these large features. If there are small features, it doesn't work quite so well. And this is again down to a resolution issue. The model has limited altitude steps and limited spatial scale. So anything to do with small things that are moving around the atmosphere, we're going to miss. That's something we have to accept. But generally, on night by night basis, the model is quite good at picking out these large turbulence features. So for the turbulence forecast then, the applications are for Q scheduling. So the most sensitive of observations are scheduled at the optimal time for that particular observation. It's also good for site characterization because if we can validate the model, if it's usable, then that means that we've got this advanced archive of weather forecasts, data going back tens of years all around the world, which enables us to look at any site around the world and estimate the distribution of these parameters we're getting. And it also enables us to reconstruct to compute our area reconstructors in advance. Okay, so as I said before, building the tomographic reconstructor for an AO system is actually really hard to do. It takes a very long time, even when you know the turbulence profile. But if something such as LTAO or harmony, for example, which is perhaps less sensitive to the turbulence profile, maybe we could do that during the day, where the strongest turbulence layers are going to be at night. So this is from a general circulation model, which means there's no specific calibration, unlike mesoscale models, but then the trade-off is with the mesoscale models you get surface area effects, you get much higher resolution data. And we've done it with coherence time, which is integrated into the cyclometer at ESO. Which brings me to the last section, which is the ELT scaling and ELT scale profiling of AO telemetry. This is with my student who actually most of the work of its label. So in this case, we take our AO system, we have our probes that are measuring the turbulence volume, and then we put it through some computer, we make a model, right? We make a 3D polymetric model of the turbulence above. And from that we can get all of these parameters that we're looking for, the how to scale, turbulence profiling. So how do we do it? Well, we start with looking at 2 stars, for example. This could be n stars, any number. And we calculate a covariance matrix. So in this case, we've got all the subaperture slopes from wave sensor 1 and wave sensor slopes 2 correlated with each other. So the diagonal is the autocovariance section, and these off-axis ones are the correlation of wave sensor 2 with wave sensor 1. So if all the terminals are the ground, it's all on diagonal. Okay. If we have a high terminal there, then we see that we get this arc up here. So this bit here tells us that there's a terminal there at some altitude. So if I go between them, you can see the difference between the covariance functions. And it's by modelling this difference that we can try and recover the turbulence profile. And so what we do is we take some data on SCIDAR, right, which looks like this. It's noisy. We have problems with temporal convergence because we need to take lots of data in order for the statistics to average. But then it changes, so we can't do that. So we're restricted in what we can do. So we take our turbulence profile and we fix it in some way to make this synthetic covariance matrix. And that includes some calibration model which is very slowly, which is offsets of your reference sensors, misalignments, rotations, and such. And it's this that's then used to build our covariance matrix. So just to show again how variable turbulence profile is, this is the same problem we saw before, but just to reiterate that it changes a lot and can change rapidly. Okay? So we need to input then the on-sky slope covariance. And we build a set of response functions which we use to then fit to this function for those different altitudes, and we give it asterism. At the moment, we also give it the outer scale, although you can fit the outer scale as well, but then you end up with some number that's the outer scale converged with or conforms with your convergence issue. So at the moment, on the telescopes that we're using, we just guess at the outer scale because there's kind of no real method of doing it. And on an 8-meter telescope, there's a project that I was involved with at Gemini. We have the 5 projects at Gemini. We can recover turbulence profiles that look like this. Okay? So this is 16 by 16 waveform sensors, so we're limited in the altitude resolution. And we can contrast this then to the data we were getting from a purposely designed independent profiler, like the SCIDAR that I showed before, that at 100 altitude, because this has only got 16 or so. When it comes to the ELT scale, we have a problem. Okay? Because at ELT scale, we have 74 by 74 waveform sensors. They have to be in double position, and we have six of them. Okay? So that's a huge matrix. This thing's really big, and then to fit to it, we have to do hundreds of iterations. So we need a way of making the problem smaller. So this is where we've always done it with small telescopes like Canary or Gemini. But actually, the slowdown technique, what we do is we take each of these sections of the covariance matrix and we reorder them in terms of baselines. So all this diagonal, for example, is all got a baseline of 0, so we'll add and then we'll apply them and that's this point in the middle. And the next one is the next point up. So now we've gone from 74 times 74 times 6 up to something which is only 74 by 74, and it's smaller than how you have been. Very big X and then Y. Then we can look at this and actually see, well, most of the information is in this bit here, isn't it? So we can just take this bit out, take these cuts out, and then we've just gone down to one vector of n points, which is significantly smaller than the covariance matrix. So in terms of the time that this takes to calculate, this is what my student did. So with the usual way of the full covariance fitting, on the Canary scale, which is 7 by 7 on a 4.2 meter telescope, you can do that in 20 seconds, that's a good time. You can afford 20 seconds. On an AOF, a facility, the UTs, which are 40 by 40, that takes 3 hours. That's the problem. So this is on his laptop, so this it's not a big workstation or anything. This is just an example of the differences. ELT scale took him 1.7 days on his laptop. They were not good days for Dougie. He sat there and watched his laptop melt away with all these calculations. I did exactly what all of you guys are thinking, which is he needs to error bars on this, doesn't he? He needs to repeat it 10 times. If we do it the new way where we use the region of interest, though, even on his 2050 MacBook Pro, he's doing an ELT scale case in 1 minute. So that's now doable. Right? This is now a regime where we can do it quite easily on a small computer. So do it on a workstation with multi-cores, and you're doing it in a few seconds rather than hours, which you would have done on GPU, for example. Okay, so it's great, it's fast, but does it actually work? Well, here's ESO's standard turbulence profile in the blue lines, and it's pinned down to the resolution of the AO system. Here it's just a canary system as an example, which is the shaded region. The matrix is the black line, and the region of interest, the fast way, is the red line. And we can see that actually the recovered profile is effectively the same, okay? Which means that we're happy that in simulation it works. Does it work on sky? Well, we can plot a scatter of the on-sky turbulence profile that we measure from the AO telemetry and the stereo SCIDAR. We see that the region of interest method, we get this nice diagonal, it's got a high correlation, so we're satisfied that we don't lose any important information when we do this baseline in the region of interest. So this is a really good step forwards towards characterization with ELT scale or AO telemetry. Which brings me on to my final few slides, actually. This is my vision of how an ELT will work, and that it will need all of these things. Right? It's going to need a combination of external independent profilers to give you the resolution and the reliability of the answer. It's going to need numerical forecasts in order to do some sort of predictive performance about which measurements to do when, about Q scheduling. And you definitely need the atmospheric reconstruction for your PSF reconstruction as well as wide field tomographic AO. Okay. So conclusions then is that in Durham, we're developing concepts and instruments to gather the maximum amount of information about the Earth's atmosphere. This includes the development of SCIDAR and SCIDAR and numerical models. And we're also looking into the turbulence scale, and put that on there because I didn't show you the results in this talk, so they're not ready. And this leads directly into ELT instrument design, not just the ESO ELT, but also the TMT now, which is particularly exciting. And it allows for AOs from a full-to-one numerical optimization, because robustness and automation are the key parameters really for ELT scale AO. And enabling PSF reconstruction is also one thing I'm particularly interested in, because this is very important for crowded field, for NCO, for anything, before I build out optics. And while I have your attention, I've got one more slide, in that we have a position for a research associate in astronomical instrumentation at the Centre of Durham, Centre of Advanced Instrumentation in Durham, which is 2 years initially, but we'll probably have an extension. And it's working on adaptive optics both for ELTs and space-based telescopes, but also in Durham we're very enthusiastic to encourage new ideas and concepts as well. Which brings me on to one last thing, which is that we have a workshop week in Durham, where we decided that instead of traveling around the world 5 times a year in order to go to workshops and all these other things, we'll have them all in Durham in one go, and everyone is invited. And if you want to know more about this purpose very line with waveform reconstruction, real-time control, AO simulation, PSF reconstruction, or want to tell us something about your particular work, then please do come on to the website. Thank you.
Okay, thanks very much, James. Do we have any questions?
Very interesting results. I was curious, when you collapsed your matrices into all the different dimensions down, how much information are you using when you do that? Because the whole point of the matrices is you can see the complicated structures, and once you've collapsed them...
That's right, yeah, and that was our worry, right? Because at first we were thinking, okay, you just ignore the correlation of X twice, probably not much in there, so we did that. And we weren't sure, right? So what we did is we did it, and then we looked in simulation if the recovered turbulence profile was different or not. And there are some differences, but if anything, it looks like by doing that averaging, we're probably increasing the signal-to-noise ratio. We're actually getting a better turbulence profile by ignoring some of that information.
For one data set, or for many different years over and over?
Yes, for many. Yeah.
Cool.
at your forecast, the lowest seeing is expected somewhere closer to the equator, right?
Yes.
So in principle, it would be best to build our telescope somewhere there, right? Would you agree? But it cannot be as simple as that. So what am I missing?
Where you're missing weather, right? Clouds, rain, all sorts of cold weather that can come from the equator.
So what is this taken into account? Is only temperature and wind, or
Yes.
what other parameters go in there?
Pressure, temperature, and wind velocity. So we're looking at wind shear and temperature shear basically as a function of altitude. So anything near the ground is ignored. If you have strong wind shear or heat at the ground, this is a problem at the equator, you're going to have radiation at the ground. And that's not included. Well, look, actually, you can, if you look at Africa, you can kind of see it pulsing a bit.
Pacific looks nice,
Yes, yes. So, you know, this is, we validated it with SCIDAR at parallel. It's a parallel and double parallel. So we haven't validated it clearly. Right? This is what I'm playing with at the moment. This is what I want to do. We'll just get more data from around the world.
Can you derive any requirements for the AO systems?
Sorry?
Can you derive already any requirements for the future AO systems for the EOT?
Any requirements?
Yeah,
In terms of
on their techniques.
update rates and stuff. Well, these are ongoing projects. So the PDR most of the AO systems due very soon. And these are all questions that are coming up in terms of how often we update our reconstructors and stuff like this. Parameters such as the number of sub-apertures in the channels, that's all fixed. Right? I think that's pretty much fixed. That's 74 by 74 is the current number that I'm aware of.
I was perplexed by one of your initial statements when you showed the cartoon that even if you correct for tilt, etc., the scintillation,
Yes.
the brightness variations are still there. Can you give a simple argument why
Well,
this is?
the scintillation is caused by the integral of the flux of the photons that goes into the pupil of the telescope, right? The AO system does not change that. The AO system changes the shape of the wavefront. It can't get more light from outside the telescope. And actually, things can worse than that, because in MCAO systems, you have to put your DMs in the correct order. If you do high altitude DM and then low altitude DM, you get propagation between those two DMs. And that can cause problems with the actual phase on the low altitude DM as well. So it's even worse than that.
So no AO systems now can correct all the simulations.
Not VO systems. So one of the things that we worked on in Durham, we've done a few scintillation correction techniques. The most promising is actually to use tomography. Okay, so we build a 3D model of the volumetric turbulence above our telescope, and then we estimate what the scintillation is from that model. Right? And then we get our scintillation signal, and we can calibrate our measurements from that. But then we're using a model to calibrate our measurements, which can go wrong. But at the moment, I think it's probably the best way of scintillation correction, but that requires a big telescope with multiple wavefront sensors. So most time resolved photometry measurements are for transits, generally on smaller telescopes. That's difficult, if not impossible to do. We can at least, with the model, estimate the magnitude of the scintillation things, which might be useful for people. Or correct rate.
Okay, any final questions? Then I think we can switch back our speaker again.